Good morning, everyone. Thank you for attending this presentation. I also would like to thank you for the organizer of this conference to invite me for this talk. I try my best to convey my topic of today, real-time Linux. So first, let me introduce myself. Right now, I'm employed in Ericsson in San Jose, California, working on telephone equipment like GPON, which is the passive optical network delivery to last mile to the broadband access to customers. That's my day-to-day job. Previous to Ericsson, I was mainly working on robotics and real-time system, as well as a real-time operating system area. So that gets me interested in this real-time Linux topic. So as you can see from this talk, I'd like to introduce what's real-time Linux and why, when you can use it and how we can use it. As you can see from this slide, there's a couple of robotics and welding tugs and then flying tugs and then listening tugs with a headset on it, which indicate audio device. So let's start. Topic, let me briefly touch on Linux as well as the real-time system, and also after that, a little bit on Linux scheduler. I'm sure most of you are active developers, so I'm sure you're familiar with the scheduler code, but to complete the story, let me cover that as well. And then the main topic of this talk, as in latency, and then all right, is this there? Sorry. And then real-time Linux, the preemptive RT patch, and then benchmark test result, and tools and tips, and then one of the things that I also involved in is the yet another new scheduler, always deadline first, and then reservation scheduler, which I was working on. So if time permits, I can cover that as well. So as we all know, Linux or Unix is conceived as a general purpose OS, so its main goal is throughput, not the latency or and real-time output. So it's for fairness as well as throughput. So that means there's not much of a determinism, and also main goal in large latency, which is most important part of the real-time OS or a real-time system. So let me go through. Real-time system is one of the talk on the other presentation a few years ago by Paul McKinley says the real-time system is not real fast system, which means even if your system is super fast, that may not guarantee your real-time performance, because real-time system is all about determinism as well as controlling your latency. So let me break down, say, roughly two types of real-time system. First, hard real-time system, which is normally mission-critical system, as you can see here, joint strike force, fighter plane, and then nuclear plants, or Mars rover system here. So in this type of system, if you miss the deadline or if your latency is more than requirements, your output is going to be catastrophic output. And there's on the other hand, there's a software real-time system as well. If you miss occasional deadline, it may affect your quality of system or usefulness of the system, degrading it. but still acceptable, like audio system or some financial stock market system or some other type of non-mission critical system. So these are the areas. The SOAP real-time system is the one that is the most prominent area for real-time Linux. Okay, so let me cover briefly on our real-time scheduler. So the scheduler is the main part of the kernel, as we all know. Decide what task or what process is going to be running next, and correspondingly allocate processor time to single CPU or multiple CPUs, and then realizing multiple tasks in a single CPU if it's a single processor, as well as supports SMP. And how you design your scheduler will impact your system behavior as well as responsiveness. All right, so a couple of years ago, there's a major rework done on kernel scheduler framework. i.e., it supports multiple scheduler classes without changing the main scheduler module. So you can plug in or different type of scheduler classes, and then that can run without needing to know and understanding other schedulers. So, for example, you have fair scheduler, which is also known as CFS, running as a main default scheduler. Also, there's a real-time scheduler, SCAD-FIFO or SCAD-RR, round robin, can be run side by side. So, and then the framework provides function pointers so that your scheduler module can run, pick up enqueue, dequeue, find out what's next, and so on. All right, so this is the depicting what I just talked about. Scheduler module has a fair scheduler, which is mainly SCAD others, CFS, and then real-time type of scheduler, which is SCAD-FIFO as well as SCAD-RR, round robin, and then there is one leftmost part is the SCAD-DL, which is the experimental scheduler. It's currently being on the LK, the kernel mailing list, trying to merge into RT patch by jury in this institute. Okay, so SCAD-FIFO is the one that first in, first out based on priority, and then SCAD-RR is same and keeps the real-time priority, but it's round robin. So every process has its own time slice, and then runs up to its time slice, and then go to the end of the queue, and then round robin. All right, so scheduler priority, there's a nice values, -20 to +19. The most nicest value, 19 being the lowest priority. And then there's a disjoint priority, which is the real-time priority from 0 to 99. Higher value is the higher priority. And then if you type PS, you will see the priority of 0 to 139, which is indicating 0 being the lowest. Starting from the 0 and the 40 up to 40, 39 is a nice value, and then after that is the real-time priority. So the table block below shows nice value as well as the real-time priority values from 0 to 99. And then what's a little confusing is here is if you type top, the priority shows on top, when you type it, ranges from 39 to minus 100, which you could just map as shows in here. So the highest real-time priority being 100 on the top, but internally also confusing is minus 139 is the lowest priority, and then 0 is the highest priority as an internal. So you don't need to remember this table. You just need to remember in real time. If you want to set your priority in a real time scheduling, just choose from 0 to 99, and then set the scheduler skep FIFO or skep RR, and then the regular other task you can set nice values from minus 20 to 19. All right, these are the system calls that you can configure your scheduler types as well as the priorities. So the first one, nice, you can set the nice values, and then most frequently used one is the set scheduler. You can set the scheduler policy, and then set parameters, and then you can get the priority max, priority mean, and then here RR get interval, so you can get the time slice of the skep RR round robin, and the set affinity. So if you have a SMP system, your process, the kernel will decide. Kernel will try to optimize the assigning of assigning your process to different processors, and however that can be optimal, but in your within your application, if you want a particular process or thread to be running on a particular processor or CPU core, then you can set this set affinity. So bitmap value, and then you can change this bitmap mask to assign the process to certain core. All right. So how to configure the priority while your process is running? You can use CHRT to change the priority, change the scheduler type as well as priority when it's running already, and otherwise you can use a set scheduler in your application. So here I was using test program called yes, which types yes, and then if you just run it, it tries to hold the whole CPU. So I just type to that null, and if I check it by typing PS, this value indicates schedule type TS is scale others, and then nice value is 19, and then since this is not real-time process, real-time priority, it doesn't show anything. And if I run to change the scheduler as well as the priority here, then you can see that FF skip FIFO, and then it changes the priority to 20, and it shows it 60 as I told you in PS output. And the top output, it shows a priority minus 21. You can go back and take a look at the mapping table that should tells you how to map it. All right. So far I've touched on Linux scheduler basics. So let's jump into latencies. All right. Latencies in kernel in real-time system or any type of application or system that you are expecting certain requirements of responses. Usually either interrupts from external hardware or timer interrupt comes, and then you're expecting your application to be responded to that interrupt, external interrupt as well as timer interrupt or timer interrupt. So say latencies in kernel when your some task is running, and then here comes the interrupt. However, your kernel or system is not aware of the importance of this interrupt, then it keeps going, and then your whatever the important real-time task that has to be responded to this interrupt will be delayed up to this latency amount. So the goal of making Linux more real-time is try to minimize or bound this latency, which will be continuing in this slide. All right. So what kind of sources of this interrupt latency? Say if some process or some modules running on kernel space, and then interrupts coming, and if that point of time, if your interrupt is disabled because it's a critical section that you want to disable interrupt to handle certain shared values or shared data structure, then however long that holds the critical section is the one that your interrupt latency. So by here, one example of interrupt disable critical section is I chose spin lock. Spin lock is the lock that instead of slipping, you keep spinning your lock. There's a various types of spin lock, but most used one is one that you also disable the interrupt while you're spinning. All right, just to touch on interrupt handler, as we are aware of already, top F and bottom F. Top F is the one that you try to finish as soon as possible, set the mask, and then acknowledge it, and then schedule your bottom F. And then bottom F will kicks on based on scheduling, and then that will perform your interrupt major handling. So, right. Now we are getting into kernel preemption. Old days kernel doesn't allow kernel preemption, meaning that when you're in kernel running some modules in kernel space, your kernel will not be preempted. So whatever the kernel module runs, that until it finished, your interrupt will be delayed or until that time. So in this example, if the prop A is running on user space, and then interrupt handler, there's an interrupt, and then interrupt handler wakes up prop B, and then based on the interrupt schedules, then next prop B will be preempted. So the latest kernel, including a mainline as well as the preempt RT, is supporting preemption. So as you can see, interrupt whenever returning from syscall or whenever moving from interrupt handler returning, then reschedule will happen, and then based on that, your higher priority process can be run after this triggered. Okay, so similar example. In this example, if your syscall was running on in kernel space, and if kernel is not configured as a kernel preemption, configured for kernel preemption, then your syscall will continue instead of your interrupt handling stops from right here. So this much is the one that delayed for the process in this case. All right, so that I covered the interrupt latency as well as the preemption latency, and there's a couple of other latencies involved in Linux scheduling, scheduler latency latency and then scheduler duration. Sched FIFO and Sched RR is using priority queue and then using bitmask to decide which priority is the highest, and then based on that you pick out from that particular queue on that priority. So that's more close to constant time scheduling. On the other hand, normal scheduling CFS is using red-black tree, which is the balanced red-black tree. So popping is popping time is constant, but inserting time and sorting that red-black tree can depends on your how many processes inside that red-black tree sorting queue. All right. So for now, I'll just briefly touch on other type of sources of latencies. So Linux supports virtual memory, MMU. So if that's turned on, one of your application is trying to get memory that causes some unexpected delays, which undermines your determinism. And also, many C library or services are not intended to design for real time in mind. Okay, so now I'm getting into what are the approaches have been done for the last maybe 10 years to make Linux more deterministic, or maybe more try to minimize the latency of interruptible processes. So there are mainly two approaches. First one is preemptive RT patch, which also known as real-time Linux. And there's other one is known as Linux extension, Xenomine or RTLI or Adios type of approach, which has extension. There's an extension between hardware and your Linux, and then you run your Linux as part of that extension. So it needs more settings and other type of APIs involved in this Linux API. In this presentation, I'm not going to talk about this Linux extension because I believe using Linux as it is and then improving it will benefit a lot more, unless you are really building it hard real-time, mission critical, and that type of application. So real-time Linux is trying to allow or make the kernel as much as preemption available, and then allowing preemption so that minimize latency, because you can preempt more, then you can respond faster than holding out preemption all the time. And I'm going to be talking about more, but many of the RT patches are already merged to mainline kernel. So the mainline kernel is already benefited by RT patch approach. So a little bit of background of preemptive RT, originally studied by some Linux companies, Tynesys Linux, Mona Vista, and then they studied it, and then at some point Ingo Manner or Thomas TLG, TLGX picked up, and then also some guys he was there from Red Hat working on this. So they are very active, and as you notice, these developers, these main developers in real-time Linux are also main developers on mainline kernel. And then companies, many companies are very serious about this preemptive RT patch set, including Red Hat, IBM, also Dell. This is the open source automation consortium, and then Linuxtronics, where Thomas is from. And their goal is improve the real-time performance of the mainline kernel. So right now it's a separate branch, not the mainline, known as a -RT. It's still residing outside of kernel, but they've been gradually merged mainline kernel, and I believe there's not anticipation is that sooner or later most of them will be merged, so that the mainline kernel can be as close to real-time OS if you configure it correctly. Okay, so main idea of this preemptive RT approach is instead of holding the interrupt disable long, you want to make make your kernel as small portion as possible so that it can be interrupted at any given time, except some critical part such as a timer interrupt and such. And also make your IRQ as also schedulable thread. So even if your IRQ comes, you can your kernel can schedule so that you can control the priority of your interrupts coming in. Also make the spin locks can be sleeping, so that so even if you're holding your spin lock, you can be preempted instead of disabling interrupt and then holding the spin lock for a longer time. And by doing so, this can be very well suited with threaded interrupt handlers. All right. These are the ones that are already in mainline kernel. If you set your kernel, mainline kernel config preempt, that's by doing so, you can configure your kernel as preemptive as possible. So all the kernel is the last one, is all the kernels can be preemptible except some critical sections. And if you use just the stock Linux from distribution, they probably be in preemptive voluntary, which just explicit some points of the kernel can be preemptive. There's other one that's also introduced by this preemptive RT patch is high resolution timers. The existing timers, the granularity is too high, and also they are not sorted based on times. They are bucketized, so the accuracy and granularity is not suited for your precision real-time application. So this high-resolution timer is introduced, and then this timer is sorted using again red-black tree, so that your timer firing is well sorted based on your timer expiration values. And also resolution is granularity, and it can be used with the mainline as well. It's already introduced. It's already merged to mainline kernel. Threaded interrupt. think I've already mentioned it, so that you can also control the priority of your thread and your interrupted threads. So all boil down to how to set your priority, including interrupt handler. Interrupt handler threads, soaked IRQs, and other kernel threads. Okay, skip this. Alright, so far I've talked about preemptive RT. So now I'm going to be talking on how we configure this preemptive RT patch sets. So where to get? It's here. If you go this link, you'll find the link for 2.6 as well as the pre 3.0 and then as well as post 3.0. Pre 3.0, you have to download the patches and you have to apply the patch. But post 3.0, it's Git based, so you just clone the Git and then you can check out the RT branch and then you can configure and then make the kernel from there right away. And I don't know how many of you have used the Yapto project, but Yapto project is also supporting RT patch. So if you download the Yapto and then you can set core image RT and the core image RT SDK, then you can build the whole system, Yapto-based system with RT patch set already enabled. Here's the link so that you can check out the reference images. So configuring the kernel, menu config, as we all know, go to processor type features, and then this is, by the way, a 3218 RT patch that I was using for this testing. So you can pick a fully preemptive kernel. This is as far as we get in terms of preemption. And you can also set the high resolution time support, and for your testing, disable power management options like these. Not all power management's bad, but you might want to take a close look if you want to use that for patch with the real-time patch. Okay, so here is the simple example of how to set your priority and then scheduler type, and then lock the memory, and then pre-fold the step, and then run the periodic test. So here we set the SCED54, which is the first in first out real-time priority base, 0 to 99. And then once you set that priority, then your program becoming a real-time task, and then runs in above the normal scheduled processes. Then lock the memory. So even if there's a memory fault comes, you can lock the memory first so that minimize the impact of the determinism here, and then also pre-fold the step. Here you can sleep, determine the time, and then you run your real-time task. And I took this example from RT wiki page here. Here's a link. All right, so talked about real-time patch and talked about how to configure it. Now I'm going to show you the benchmark result. So one that I'm using is a cyclic test, which is using a high resolution timer, so that make sure how long is the latency that you from your design time periodic running. So here I got the testing suite program from this Git and then running it as on the old core, and then running it as priority 99, which is the highest priority. So this is the result from a core vanilla stock kernel from Ubuntu, and the setting is preemptive voluntary here. So the one thing that you want to focus on is, this is talking about this kernel, and then the rightmost value, which is the maximum value of latency of how these threads are running, which is hundreds of microseconds here. And now I'm going to move to the same benchmarking test. Excuse me, benchmarking test on preemptive RT patch. Same PC with the 8 core, and then I'm running 3218 RT patch applied. So here the maximum worst case latency is tens of microseconds instead of hundreds of microseconds. That's a huge difference in terms of determinism or the controlling your worst case latency. So now I'm going to run the extended test, which is using the same test and running in different priority over 1 hour in this case. And this is the histogram of the run of the regular kernel, the vanilla kernel. And the maximum latency is 325 microseconds. Average is 7 microseconds. Same test run on the preemptive patch. The difference is the maximum value is a lot lower and it's controlled. So same test running on 2 hours. The vanilla kernel even gets worse, 940 microseconds, and the real-time patch is still under tens of microsecond range. So this was my test, and then there is the QA farm, what they call. They in osodal.org, they have testing farm they have tens of different PCs and embedded board. They are running every day, overnight, running a different type of preemptive RT patch. So this is one example that I took from them. One is, okay, the right side is from the regular kernel, and then the left side is the preemptive RT patch. And as you can see, the maximum latency is quite different in these two examples. If you can go to this link, you'll see a lot more result, and then you can also see the live result from this, also the QA farm. Okay, so far, as far as I know, these are the few examples of RT patch that are deployed. I think US Navy Zoomed total ship computing environment system, which is done by Raytheon. The main reason that they choose a real-time patch for this TSCE is, one thing is they need some system that is maintainable for longer time, and also they need to have some soft real-time characteristic is required, because this is not the critical part of the ship control, but it's something that computing the environment of the ship, so it should provide the minimum requirement, and then worst time execution cases. So that's why they choose Linux for long-term maintenance as well as and also the real-time characteristic. And the next one is, this is pretty new news. U.S. Navy VTOL, vertical takeoff and landing drone is deployed by ground control, Windows-based ground control, but there was some malware infected last year. So I think that's why they choose Linux for ground control of this drone. So it's going to be controlled by Uncle Linux instead of Uncle Gates. So this is also contracted by Raytheon. So I think it's going to be the real-time patch as well. So this is too new, so I didn't confirm that it's a real-time patch for this. It's released I think yesterday. The other one is the laser cutting and welding done by a German company. They use the Linux RT patch for controlling their laser cutting system. And a lot of robots, and this is one of them called Now, dancing and synchronizing robot. All right, so roadmap. The first thing is complete full patch merge to mainline. Well, yes, we can only guess. So this is what Linus says, 2010. Yeah, I think the hard real-time people are mostly crazy. So it should be read as getting close, but might take a little more time. However, also he said, real-time people have actually been pretty good at slipping their stuff in small increments, and always be good reasons for why they're not crazy. So it should be read as small and well-defined piecewise stuff can be still merged in. So it's, to me, it's quite promising. It has been very actively working on patch sets, and then also quite a lot of them are already merged. So I think we can expect this to be merged sooner or later. Performance tuning tools, ftrace, function trace, developed also by one of the RT preemptive patch developer, Stephen, and it's very well documented. And he even made a GUI tool for displaying this ftrace. Kernel shop, what he's called, similar to Wireshark in network hacking browser. And this is Tuna from Red Hat, which I have not used it because it's part of the Red Hat MRG real-time package. I believe you have to subscribe to get this one, but it looks promising, so I just put it here. And the other regular performance tool, tuning tools for profile, which is system-wide statistical profiling. All right, so I talked a lot about the real-time Linux patch sets, but all boils down to how you define your priority of your application in order to control your response time. So the simplest thing can be the rate monotonic. If your application or programs mostly running periodic or have to run every certain period of time, then you can just decide your priority based on the period of the application. So the more frequent, assign the higher priority. It's simple, but it guarantees the schedulability of roughly 69%. If you make sure your CPU is utilized up to 69%, then this schedulability guarantees that your processes can be scheduled. It's very simple, but I think it can be useful for certain applications. And of course, you need to try to measure worst case response time, and then based on that, you need to tune your priorities. But try not to use sched FIFO scheduling with 99. If you use this, your process can hold the whole system if you don't, if that misbehaves. And try to find the hotspots using profiling tools, profile and profile, and then measure and estimate the worst case execution or response time. And also you can control your process affinities. So for example, if you have example that's some thread sending data and some thread consuming the data, you don't want to put them in the same thread. You just put them into different cores instead of the same core. Okay, one thing also I want to touch on is the response time and throughput. They are opposite. In other words, your response time is more deterministic. That means your throughput can be lower. So that is expected. In other words, if you use the preemptive artifacts, your performance can be slightly decreased because it's more preemption, there's more context switching, and there's overhead involved. So that is expected. However, the main point being here is the determinism or the lower latency. All right. I'm going to be quick on this topic. I think Linux is good, and I like it because it opens up a lot of opportunity to bring the academic research into the real practical application. This is one of the example that EDF, always deadline first scheduling method, that has been talked about more than 10 years in academia, but non-commercial operating system had maybe one or two, but not in popular major real-time operating system. However, there is an actual attempt by teams in Pisa, Italy. They implement this EDF, always deadline first scheduler, and then the reservation-based scheduling system into mainline Linux. So always deadline first. Instead of assigning priority, your task is scheduled based on the deadline. So if your deadline is closer, then you will be scheduled. So it's a dynamic scheduling. So it depends on how far is your deadline. It can be scheduled sooner or later. So that's the main idea of this. And also, in addition to that EDF, there is also, you can apply the reservation-based scheduling, which is you look at your CPU as a resource and you assign the percentage of the CPU, so that even if you want to use more than such and such percentage, your scheduler will limit it to that assigned percentage. This is an example that I run the same IDS example. I said the first one 30% assigned, second one 20%. As you can see, the utilization is around the reservation that I assigned. So it's been, I think, take 5 of patch was sent to a mailing list. So let's see how that comes along with this one, this particular EDF deadline-based scheduler. So please tune in. It could be sooner or later merged into a real-time patch. So the summary. So most important in real time, try to make sure. Say this is your before preemption patch applied over effort. So everything is just a big chunk, but after effort of this real-time patch set, you make your critical section smaller so that at any given time, if interrupt comes, then the corresponding interrupt handler can be scheduled instead of waiting the long latency, unbound latency. That's the main idea. And if you use mainline kernel, you could use the config preempt and then skip FIFO, skip R with proper priority. If you use preemptive RT patch, then it can be virtually everywhere can be preemptable. So last take is Mr. Tobo says, so I can work with crazy people, meaning real-time people. That's not the problem. They need to sell their crazy stuff to me using non-crazy argument and small and well-defined pieces. Right, so these are the references that I referred for this presentation. The links are here, so you could look at it later. And the web link. And disclaimer, this doesn't represent view of Ericsson, just legal stuff. And thank you for your attention. And any questions?
Since many real-time pages are merged in kernel, what is the impact of the business device drive model? I mean, consider the threaded interrupt controller and the overhead real-time preemption.
Mm-hmm.
So, drive model might be changed, right?
Yeah. So the question is, since many of the real-time patch has already merged to mainline, so what is the impact on the driver model? I think the real-time. Well, I think the straight answer is it's manual, so you have to make sure the driver model works fine with the real-time patch threaded interrupt model. But the real-time patch side, the branch, they automatically change all the threaded interrupt, at least for the architecture they support x86 and ARM, but I think the other architecture and other drivers that are not touched should be manually examined. I think that's as far as I can answer your question.
But can you back to the opinion of Linus Torvalds? I mean, the summary crazy. So Linus Torvalds is against the.
He was against the priority inheritance as well, but after he openly said you're not gonna check in the priority inheritance mutex to the kernel, but that has been already merged maybe a couple of months later after he said. So he's coming from different direction, as in desktop server, those areas. But if you need the Linux to be more real time, it's a matter of how to convince him.
那我们谢谢那个马英楚先生。